All right, so in this lesson, I want to talk a little about linear programming. You'll get an idea of what linear programming really involves as we go along. It's good to know where it all started. This was, you know, a method that was introduced um, during the World War II in particular. Um, During that time, the need for countries to really economize the resources they have, uh, that came to the fore, right? They had to find ways of minimizing the material they're using for production of everything, including weapons and all of that, as well as maximizing damaging the uh, the enemy as well. Um, over the years, though, right? These these ideas of you know what we call optimizing the use of resources and to create the greatest amount of profit was applied more to business, right? So it started early, right? It started early, um, but eventually it was put to good use in business and economics, right? Um, One of the early problems that we dealt with during the war was what we call the transportation problem. How quickly things can be moved from one place to the other so that you can really reduce costs, time, and so, right? Later on, I think somebody applied it to diet. I'll try to probably either here, not so much here, probably limited amount of time, eh? Maybe in the tutorial, I'll either cover one of the transportation problems or the diet problem. I'll try to cover at least one, right? And as a matter of fact, though, I want to tell you that linear programming, the work that mathematicians did with it, led to a couple of them. So, was Russian guy. Yeah, he was Russian. The other guy was, I think, hmm, he's American. They won a Nobel Prize for their work in linear programming. So this is Nobel Prize kind of stuff, right? But I'm going to just introduce the thing to you, right? I'm going to introduce it to you. First, we're going to deal with a graphical approach to solving the problem, which is very, very easy. It's really nice for those who came out from CXC. And, they're used to drawing lines and graphs and so on. So this part here especially will be very, very simple for you. And you will not have much trouble with it. And later on, I'll try to, I don't feel very comfortable doing it with you because it's a rather complex thing. Um, Somebody came up with something called the simplex method, right? He was an American guy. He came up with something called the simplex method. It's not simple in any way. It's related to matrices and some row operations we used to do on matrices and so, which we didn't do, which we couldn't do because of time. Time. This kind of thing you want to do in a whole semester, not just a couple of weeks, right? So he came up with something called the simplex method, and we will cover that. I'll probably give you a video, maybe from YouTube that was nicely done. And in the tutorial, we're going to do a couple of examples so that it becomes clear to you, right? But before we get into linear programming, I want to review a little bit of stuff on, make sure, second. We want to talk a little about drawing lines and uh, drawing, you know, inequality, and looking for the area that satisfies the inequality and so on. Right? So I'm going to review that quickly. So let's let's say you have a line, you have a line. The line is x plus y equal 5. How do you draw this line? How do Well, the easiest thing to do is to make up a little table. And to draw a line, you only need how should I put it like this? X and Y. All right. You only need 2 points. So let's say x is 0. If x is 0 here, y will be 5. And if you put y equals 0, x will be 5. You have 2 points here. You have 0, 5, and 5 is 0. Right? And you can put that on a graph very easily. This is 0 here. 5 here. 5 here. Right? And that line looks like what? 0, 5, that's this point. 5, 0 in this point. And that line looks like this. Right? I'm going to go over to Desmos just now. To draw it with a piece of software, right? Desmos is a nice online calculator, graphing calculator. So it's going to do it much neater than me, right? So this is the line. You just have to take any point for x, calculate the y back, right? You can take another point value for x and calculate the y value. Shouldn't take long, right? You get 2 points. Doesn't have to be the numbers I use. You can use any number. You can use x equal 1, x equal 10, equal whatever. You use any number. Calculate the corresponding y value. Get the 2 points. Plot it. That's your line. Related to this, so let's say you have this inequality line. That line is straight. All lines, any line is over like whatever. Right? You can use this method. Quickly sketch the line. So let's go with all right. Let's say you want now x plus y. Uh, uh, is less than or equal to 5. Right? So we don't have an equation anymore. We have an inequality of values, right? So one home, well, okay. Which region here satisfies this inequality? So this is what I'll do. I'll just choose a point, either below the line or above the line. Right? Just choose any point. Right? So I'll choose the origin. Right? Origin. And that point, the origin here, kind of represent all points below the line. And if you do that, you see what? 0 plus, but the origin is x equals 0, y equals 0. Is less than 5. That's true. Right? True. Therefore, everywhere below here, is going to, there are all the points below that line here will satisfy that inequality. And you can try it. You can try it, right? You try a point here, try a point here. Any point here, you try any point. Right? I think some textbooks will say instead of coloring up all here, most of the software program is going to be color up below here. I know when I was a young boy at school, they tell you, shade this over a little here. Meaning, when you do this, you really mean that the opposite side is the feasible regional part, right? Or that region satisfies the equality. We will come to that word feasible region in just a minute. Right? That's a little heavy at the moment. Right. So let me maybe pause the video. I want to go to Desmos to see how it will look, right? Let me do it. Good. So here I am in Desmos, right? And I'm going to remember that graph that I just showed you. All right, so we had x plus y equal 5. Look at it here, right? That's x plus y equal 5. So that's it. Right? So let's go with, remember I said x plus y is, let's say less than, go with less than or equal to 5. See what happens there? They actually color up the entire region below the line, right? And that's the region that will satisfy that inequality. Any point here, you take any point below here, you put it in that inequality, it will satisfy that inequality. So it's how powerful Desmos can be, right? With just a couple of clicks, couple of typo, you type a couple of numbers and you can get it. But it's good to know, like I showed you on the one slide here, it's good to know how to plot a straight line, right, with hand. We all want to have that kind of knowledge because you don't always have, these kind of software every year and all of that, right? So, yeah. Let me pause the recording again. Go back to. So we are back here. Okay. So these are some steps, that you want to make use of when it comes to solving problems, in this topic area of linear programming, right? So you'll be given a problem. Read it really good, as you want to really understand what you're asking, right? Next, you want to define the variables. We'll see how to do that in a little bit. A problem in just a moment. And they say find the objective quantity, right? Because oftentimes your objective is going to be maybe maximizing profit or minimizing cost, that sort of thing. Always either trying to maximize something or minimize something, right? You have to come up with a little bit of an inequality really that would kind of spell out, what you want to maximize, what you want to minimize, right? And then they talk about constraints, right? These are any problem, they'll give you some kind of conditions, that you want to meet. And then you will attempt to graph the inequalities that you're given. I just used the word earlier, feasibility region. I talked about feasibility region, right? And you'll see that there's this theory, right, that the maximum or the minimum will occur at what we call the corner point. So that's 0.7 there, right? It can happen along any one of the sides, right? But we're not going to get into that. We're going to use the corner point. And then we can be able to answer, well, the question we started off with, right? Because most of the time they want to know what's the maximum profit or minimum cost or whatever, right? Yeah, you will be able to answer the question after some amount of calculations, right? Good. So let's see a problem. So I'll leave it there for a moment. So you can be able to problem. So here's a problem. So, well, this is the business problem, right? This is more like a student problem. So you're taking a test. Speaking of test, I think you all did much better in this test than the previous one. You get into test taking. There are people with even 40 and so 40, 42, 44. You do very well in this test. There are a few who, no matter what, will have those. Yeah, so this is test taking. You're taking test. You have type A questions, 10 points each. Type B questions, 15 points. Type A questions takes 3 minutes. Type B questions take 6 minutes. There's a time constraint, 60 minutes only. And there's also a number of questions too that you can answer 16, maybe that's the whole test, right? And well, here's an assumption here. You know, these are things you have to get all right. How many of each type should you answer in order to get the best score, right? So you go through the steps. You want to define the variables, and maybe we could say, um, maybe you can say let let x be the number of type A questions. Let y be the number of type B questions, right? So there's some information there. What did I say? One type, I think type A takes 3 minutes, so that'll be multiple choice. So 3x, right? 3 minutes times the number of type A questions that you answer plus 6 minutes type B questions take. So 6y all must be less than or equal to 60 minutes, right? So that's a constraint. All right, right? And then they mentioned that you couldn't answer more than 2, right? Sorry, 16. So yeah, they must add up to be either 16 or less. And of course, you can probably add in some other than x must be greater than 0, right? Y must be greater than 0, right? uh, because you wouldn't, go into a test and not answer no question from one of the sections, So how can we graph? Right? How can we graph? So I'm going to graph it on decimals, right? I'll graph it on decimals. I wouldn't use this here. So I have to go over the decimals. Give me a second here. Good. So here we are in decimals. And we want to graph all the conditions, let's go with what are 3x plus 6y must be come down here less than 60. So that's what that looks like. Okay, one graph, another condition. X plus y must be less than 16. Right? My graph is getting ugly. Right? Graph is getting ugly. And there were the other two. I don't want to put them in because x is greater than 0. Ooh, no. That's gonna make y is. Why can change these to lighter colors? Y is greater than 0. Wow. No. Oh my. It really messes up the graph, right? Really messes up the graph. However, from the graph, you can actually see if I can annotate on this. Annotate. Let me annotate. So what this is saying really, right? That this area here is, I'm not drawing very well, right? This region here satisfies this region here, right? This region here, all here. Any point in this region satisfies all these inequalities, all four, right? So what we're trying to do now is we want to find what was the maximum score, right? So our objective function was this. I think I should have mentioned that We didn't talk about the objective function at the beginning, right? So they say that you get 10 points for any type A question that you get right, and 15 points for type B. So um, you want to maximize this, right? You want to maximize P equal, let me use P, right? Or if you want to use M as max, you want to maximize 10x plus 50y. You want to maximize that, right? Good. So what you'll do is substitute each of these points here. You substitute each of these points, corner points, right? But there is a theory that says the maximum will occur at one of these corner points, right? At one of these corner points. There are situations, I'll tell you, where you have a maximum of more than one corner points and all that. We're not getting into that level, right? We're doing basic ones where one of these will give you the right one. Oh, by the way, these corner points can actually be calculated rather than put on a graph, right? You can actually solve this equation here, this one here, and this one here simultaneously, and you will get this point here, right? And we can actually get the points of, we can actually get the points of, I can click here. Wait, I might have to erase everything. Let me erase everything. Everything. Oh, you got to remember this one, right? Stop it there. Can't erase that yet. P equal 10x. This is what we'll be maximizing, right? This here. Now I'll come back to that. 10x plus 15y, right? We're maximizing that. So we want to get these points, right? Get these points. Let me erase and so I can actually get those points. So I think you're going to click here. You can click there and get the point, right? Then you can click here. Yeah. Yeah, that point. You can click there. And get that point, right? You can click there. They will come up in the corner there. You can click here. All right. Good. So they're all here, right? And I'm not going to go through the whole process. What I'm going to, if I substitute, you will find if you do it. Oh, oh my. Yeah. What happened to my point? Oh, yeah. So those are the points again, right? And remember our what you call it, the objective function that we're maximizing, or that's going P equal, what was it? 10A plus 15. Why is that it? 10A, this is the question. 10 points for every question you get right of type A and 15, yes. So if you substitute these numbers here, this one, 0 for, what am I writing here? It's supposed to be X. Yeah. If you substitute 0 for X, 10 for Y, you can see, well, 0, 0, you do 0. 16 for, remember you have to do more than what is one, right? So these points really couldn't work, right? So you have to substitute these 2 points. And that will give you a maximum of, somebody can type that in, what will you get that? You'll get what? 10 by 12. So I think you get 180, huh? If x equals 12 and y equals 4, p will be equal to 10 times 12 plus 15 by 4. That adds up to 180, 180, right? Uh, and that then is a maximum amount you can score in a test, right? So if you answer 12 type A questions and 4 type B questions, that will give you your highest marks, given the other constraints that are here, right? So if you're taking a test under those conditions, that's what you have to aim to do. So again, I'm going to pause the recording because I have to go back. I'm going to take another example. Good. So let's look at another. This is more business, right? Uh, so you're taking a furniture dealer dealing with two types of items: tables, chairs. Again, I'm noticing a lot of Indian writers are writing about these subjects on the internet. I'm finding a lot of Indian writers. So this guy is putting the money in rupees, right? So 50,000 rupees he has to invest. That's a constraint right away there. He doesn't have more than that. That's what he has to invest. And then storage space is another constraint. 60, you can only store 60 pieces, right? A mixture of table and chairs. They give you some costs here. Table, $2,500, chair, 500, right? And then if he sells, what is this on a table, he makes 250 as a profit. If he sells a chair, he makes $75 on one of them, right? So he wants to know how many tables and chairs he should buy from the available money so as to maximize his total profit. You see, typical. You have a certain amount of money to invest. Uh, you have these items that you can stock, you have storage constraints, you have how much money you have to invest, and you want to know, well, what is the optimum number of things you should buy to store in this thing when you're putting a store or a business so that you can make the maximum profit, right? So that's our, of course, this is an oversimplified situation. You got so many other factors, right? We, remember, we are only dealing with very oversimplified problems, right? You never know, there's a higher demand for certain things and it might make more sense to buy more of it and so on. That's not what we're talking about here, right? We're just highlighting that we're okay. He has the demand does exist for both tables and chairs, right? And when he gets them, he's going to be able to sell them within a certain period of time. All of that, lots of assumptions that uh, is in the problem that sometimes not, explicit. Good. So let's take okay, the same problem. So all right. And he wants to maximize his profit. So this is the objective function here, z equal 250x, because he's making $250 profit on a table and $75 from a chair. So his profit function, or his, what we call it, the objective function. The objective is to maximize z, right? Your objective is to maximize z, which is your objective. Make the most profit. So these are the constraints, right? What do we have here? Where do you get 5x plus y must be less than or equal to 100? Now, where do you get that from? I think he got that from, let me just annotate again here. Give me a second. All right. Your investment is 50,000. table cost 2,500, this cost 500. So okay. So if he buys X amount of tables, that will be 2,500 X plus. Right? And we're letting X, notice X and Y be the number of tables and Y be change, right? So, and then if he sells 500 or buys, sorry, 500, Y amount of chairs, you have 500 Y, that must be less than or equal to 50,000, right? And what you do, you divide everything by 500, right? Divide everything by 500, you get 5x plus y is less than 100, right? 100. And that's really not that complicated. You know, these textbooks, they assume you know a lot more than you do. Well, this one isn't hard. This one is a space constraint, and you're going to put in these extra two, meaning that yes, you'll buy at least one table and one chair, right? At least, yeah, more than one, right? So let's say more than zero, right? So let me take all of this. Let me take all of this. Let me erase them back. Take all of this. And we put it on a graph, right? All right. So yeah, this is just to summarize. I think there's an error here. What's happening here? What's here? There's something here. I think it's supposed to be. Let's go back. All right. Here. Yeah. Good. So you take all these now, right? You take these. But remember this one here breaks down to, what was it we had? X, 5x plus y is less than 100, right? You got that. I'm taking this, and this. I'm going to put it on a graph, right? You can graph them all. Good. Oh, sorry. So that's your graph, right? This is not Desmos. This is just, I took it from this writer's textbook, right? That's his graph here. So this line here is the line 5x plus y, x plus y equals 60 is this line. Well, the x-axis is the line y equals 0. The y-axis is the line x equals 0. And this shaded portion, if you were to do this, you can go through the pieces, right? You can go through the angle. You could take a number like, okay, let's take this one, 5x plus y equal 100. And you can choose the point 0, 0, and you substitute it in there. And you will see that, well, 5 times 0 plus 0 is less than 100. Therefore, below the line is the region that satisfies your inequality, right? X plus y equals 60. If you choose again 0, 0, you see below the line, right? And the intersecting shading, right, will be this part here. Because, okay, you have to get x is greater than 0, y is greater than 0. So that will kind of give you this feasibility region. You can use Desmos, no problem. And you put it in, you put all of this in. What I don't like about those software programs is when you finish, you shade up the whole thing. And it's kind of crazy interpreting, you know, which really is the feasibility region, right? It makes it difficult sometimes. Good. And after you have done that, you identify the vortices, right? So they give you the vortices. Well, we're not going to use 0, 0. You know, that wouldn't do us any good. This point is 20, 0. We have a point 10, 50. And we have a point 0, 6. And I want to tell you, as we said, in the, you would think that the person would buy at least one table or one chair, right? So those points with zeros may not do the trick, but it's good to try them, right? Try them. And then you have the 10, 50. The maximum will occur, maximum or minimum will occur at these nodes, you know, these corner points, you call them nodes or corner points, right? And if we were to put them in the function, what we have to maximize? Z. Let's see for Z. Remember Z? What was Z? Can I go back? I might have to go back to get Z. Z is 250x plus 75y. Right, so Z is equal to 250x plus 75y. And the reason why is that you make a profit of 250 on each table. You make a $75 on each chair, right? So you take each of these points, substitute it there, take each of them, and these are the outputs, right, of Z. And you can see them. This is going to be your maximum profit, and it will happen if you buy 10 tables and 50 chairs. Right, and we're going to do, I'm going to ensure that we do more than one of these in our tutorial, right? I'll probably do 2 of them, right? I'll probably do 2 of them. So the problems would vary, but the very basics is the steps I showed you, right? Make up your inequalities with your constraints that are given. Get your objective function, graph all your inequalities, get your feasible region, get the corner points, substitute them in your objective function and see which one produces a maximum, right? As a little practice, maybe, okay, look one here. I don't need erase all this. As a little practice, this is not a practical problem. You just get we have some conditions. And you have to minimize. Notice this wasn't something to deal with a maximum, but a minimum. Let me write them down and go over to Desmos. Right? Find a pen here now. Ooh. Give me a second. Pause the recording. I gotta go find a pen. So let's go over to. I got a pen here, so I write down the conditions. Maybe you should, right? You should also go note it down. So let me go over to Desmos, right? So we're going to plot the inequalities x plus 3y greater than or what? Greater than or equal to 3. And then how is it? X plus y must be greater than or equal to 2. So this is the region here. Greater than. You know what? Putting in the other two, x and y, they will only color up the diagram, right? X is greater than 0, that will only color up the whole diagram. So I'm not going to put any, right? I'm not going to put any. So what you're seeing here, this here, see this point, exactly where they intersect, right? That's this point, okay. This point as well. And this point. So this feasibility region, right? It's like an unbounded region. It isn't bounded like the others. So we need to try these numbers, 0, 2, 1.5 and 0.5, and then 3, 0, right? And we have to put that in. Let me see if I can probably annotate right here. We have to maximize what we do. No, we have to minimize something. We have to minimize. We have to minimize z. I'm working here. Z equal 3x plus 5y. Right, so let's see. If we put the 0 this in, you will get, okay, z of 0, 2 would be 1. 3 by 0 plus 5 by 2. That gives us what? 10. Okay. We go to the next one. Z of 1.5 or 0.5. Let's see what will happen. 3 times 1.5 plus 5 times 0.5. What would that add up to? 1.5 by 3, 4.5 plus 2, 5. This will give you 7. And the third one I'll do it here. Z of 3, 0 will be what? 3 times 3 plus 5 times 0. And you get 9. So the minimum value for Z will occur here. Here, right? When this here, at this point here. Right? The minimum value for Z will occur there. See? So when you have x equal 1.5, y equals 0.5. I'll try to see if we can find one or two more in some piece of literature for us to discuss in the what I'm saying, tutorial. Yeah. All right, so yeah, that's linear programming in a nutshell there, right? Linear programming in a nutshell. I'm going to see if I can find an example of two more, maybe on YouTube, and paste it on to the end of this video so you can watch more examples. And YouTube is so full of them, right? So full of them. But I'll do that. I'll paste on a video or two so that you can watch some more examples.
In this video, I'm going to tell you about a very powerful optimization technique called linear programming. Now, I know it has the word programming in the name, but we're not actually going to be doing any sort of computer programming here. And in fact, we're not going to use any high-level math at all. Calculus, linear algebra, none of that. Instead, we're going to use a very simple geometric technique that somehow manages to solve this very important class of optimization problems. So what are we talking about? What I'm imagining is I want to optimize the value of some function like this, 180x plus 200y, something like that. That is, this is a linear function of multiple different variables, say x and y. This is just an example. What does optimize mean? Well, it could be find the maximum or it could be find the minimum, but we're not just optimizing this function by itself. We're optimizing this function subject to various constraints. For example, I'm just putting up some random ones, a series of what we call linear inequalities. Things like 5x plus 4y is less than or equal to 80, or 10x plus 10y is less than or equal to 200, or x is positive, or y is positive. Those are all linear. There's not an x squared or a sine of x, but they're linear inequalities. So this is the idea of linear programming. You're trying to optimize some linear function subject to a list of linear constraints. To give an idea of where this type of problem would come up, I'm going to share something called the Carpenter problem. The idea is this. A carpenter can make tables or they can make bookshelves. If they choose to make tables, it takes 10 units of lumber. I don't know anything about carpentry. I don't know what a unit of lumber is. Some cubic meter. I have no idea. It takes 10 units, however, of lumber, but it takes 5 hours of their labor. And if they make a table, they're going to make $180 profit. Alternatively, if they decide to make a bookcase, well, it takes twice the amount of lumber to make a bookcase in this, again, made-up scenario. But it takes less time for whatever carpentry reason. Again, I have no idea. The claim is that bookcases are perhaps easier to put together. So 4 hours of labor, but you make more money, $200. Okay, and then there's a few other constraints here. First of all, is that there's only 200 units of lumber available that we can make our bookcases or tables out of. And finally, in, say, 2 weeks, you want to work only 80 hours. There's a constraint that is on the amount of wood, and there's a constraint on the time. Okay, so my first task is going to be transition this word problem into the system of equations and inequalities like what I just described. So let's let x denote the number of tables, in which case, if you make x tables, you use 10x units of lumber and 5x hours of labor. Likewise, I'll use y to denote my number of bookcases, and so 20y is the amount of lumber I use, and 4y is the amount of labor that I use. So if I condense these equations down, then the question, first of all, is, well, what am I trying to optimize? Well, I want to make as much money as possible. That's the goal here, right? So what's my money going to be? Well, I make $180 for every table that I make and $200 for every bookshelf that I make. So the thing I want to optimize is this function, this linear function, 180x plus 200y. Okay, so what about my constraints? Well, first of all, let's think about the constraints on my labor, the number of hours that I can spend on this. So the rule is 5 hours for a table, 4 hours for a bookcase, and as a result, 5x plus 4y has to be smaller than the 80 hours that I'm willing to work. Then, if I want to consider the constraints on the lumber, well, then 10 times the number of tables plus 20 times the number of bookcases has to be less than the 200 units of lumber that I have. Again, another inequality. Finally, the number of tables I make is going to be a positive number, and likewise for the number of bookshelves, I'm not going to make a negative number of tables. Okay, so now I want a procedure to be able to solve these, and I'm going to introduce something called the simplex method. But before I do that, I just want to visually understand what are these inequalities actually saying, and for that, we turn to the computer. To help me graph these inequalities, I'm going to turn to Maple Learn, which is actually the sponsor of today's video. If you go down in the description, you can check out for free either the web application Maple Learn or the phone-based app, which is the Maple Calculator. Both of them are pretty cool and allow you to do the following thing, which is to graph an inequality. So what are we trying to study? Well, we have the first inequality, 5x plus 4y, and that was supposed to be less than 80. And what we have on the right-hand side is the plot of this inequality. And the idea is that along this line, this is the equation 5x plus 4y is equal to 80. So the fact that I'm asking less than 80 is going to shade in this entire green region, which is the portion beneath that line. Okay, that was one of our equations. What was the other? It was 10x plus 20y was less than 200. And now what you see is two different regions. Let me just go and zoom to the right location. And what I now have is these two different linear inequalities at the same time. I have this first line and the portion underneath of it. And I have the second line and the portion underneath of it. And what we have in the dark green is the region that is less than both of these particular lines. This is the region that we're going to focus on in this video. Okay, so this is the image that we got, and I've highlighted around in yellow a region. And the point is that this region is identified by these different inequality equations. So we had the 10x plus 10y is less than or equal to 200, which is bound by the equation where it's equal to 200. That's that sort of top side. Likewise, I have 5x plus 4y is equal to 80, again, the boundary of the other region. The final two boundaries are x equal to 0 and y equal to 0. I'm only making a positive amount of tables. What these four edges do is they bound something called the feasible region, or the feasibility region sometimes. And the idea is this. Any value of x and y inside of that quadrilateral is possible. It doesn't violate my constraints. It's both less than or equal to the 200 in the one equation and less than or equal to the 80 in the other equation. and positive for the x and the y. That is, the value of x and y that satisfy the constraints all live inside of this yellow region. Okay, but which of those points in that yellow region is the best? Which gives me the most amount of money, which maximizes my linear function? Now, I want to note here that there's 4 different vertices to this region. That corresponds to the fact that I had 4 different inequalities. If I had more, I might have more vertices. And I'm going to try to persuade you by the end of this video that the maximum value, and the minimum for that matter, has to be one of these vertices. And in fact, I think we can do a little bit better intuitively. I think it actually has to be only this middle one. I mean, clearly the 0, 0 vertex is not going to be the maximum of the money that I'm going to make. I haven't made anything at 0, 0. But this idea is this. I have 80 hours available of labor, and I have 200 units of wood. If I use less than the 200 units of wood, I would have preferred to use more. I could have made more money if I used that wood in some way. Likewise, if I use less than the 80 hours of labor, I could have made more money by increasing that. And so, intuitively, what I want to do is find a spot where I'm using all of the wood and all of the labor, and that's going to give me the most amount of money. And indeed, that vertex point that we've identified here has these 2 properties. It's on the line, which is you using all 80 hours of work available and all 200 units of wood that's available. And so I think this vertex specifically is likely to be the maximum. Again, I do owe you a slightly more persuasive argument for that. That's going to come up a little bit later in the video. Okay, but if you're with me for now, how do I find out, well, what is that vertex? What is the location of that vertex, and how much money do I make at that vertex? So really what I want to see is I've got these 2 different equations here. So the equations say I'm actually on the line. I've used the full 80. I've used the full 200. It's not less than or equal to. If I solve both of those for y, well, the top gives me y is 20 minus 5/4 times x, and the bottom gives me y is 10 minus x divided by 2. If I'm interested in the intersection point, I have to set these 2 values of y to be equal to each other. And doing this, I can solve for the value of x. X is 40 divided by 3, or about 13.3. And likewise, I can take the value of x, plug it into either equation, and get that y is 10/3, or about 3.33. The next thing I need to do is figure out how much money do I make with these 2 values. At this number of tables and this number of bookshelves, how much money do I make? Well, my function that I was considering was the function 180x plus 200y. That gave me the amount of money I was making for the number of tables and bookshelves. Plug those in, and I get 3066.7. So that's how much money I'm going to make at this, what I'm claiming is optimum value. Okay, so let's turn back to our graphs. So the claim here is that at this vertex, which is located at x value, the number of tables being 40 over 3, and y value, the number of bookshelves being 10 over 3, I'm going to make this $3,067. The other intersection points are also kind of interesting. For example, the one which is you do 0 tables and do only focusing on bookshelves makes me $1,800, not bad. The other version, which is where I only focus on tables, I don't make any bookshelves, gives me $2,880, much better. But notice that both of these, as we predicted, are worse than the optimal value of the 3,067. Finally, should be no surprise, if I make 0 tables and 0 bookshelves, I'm going to make $0. Now, this is actually important because this method is going to optimize the function. And so that's going to be able to tell us the maximum and the minimum is going to occur on a vertex. So the maximum will be the 3,067 and the minimum will be 0. Both of those are vertices. Now, I'm going to go back to MapleLearn for this next point, which is I want to go and plot this function that I have, which was 180x plus 200y was equal to 3,066. You put all of that in, and I have to go back over here and scroll out so I can see it. And what this new addition of this 180x plus 200y is equal to the value we computed, the 3,066, is it plots this blue line. And notice that that blue line goes exactly through that intersection point. Okay, now bringing it back here, this line that we're talking about is called an iso value line. That is, this is the equation 180x plus 200y is 3,067, as we talked about. And so what this means is it's all values of x and y such that you get 3,067. In other words, an ISO value line is one where the value of the function, the amount of money you're going to make, is just going to be some constant. Like perhaps I'll just replace this with a constant c. So imagine, if you will, what happens if I increase the value of c. So I'm going to make it bigger. I'll bring it up here. Well, if I do that, this is a larger value of c. Notice that it no longer intersects with the feasible region. That is, it's a larger value of c. You'd make more money. That would be great if you could get there, but there's no feasible x and y that allows you to attain that larger value of the constant. Similarly, if I bring the constant down, so this is now a smaller value of c than 3067, well, there's all sorts of points in the feasible region that give you this particular value. All points that have this line, this ISO value line, but the c is smaller now than the 3067, and so you make less money. So yes, it's easy to make less money, but you don't want that. You want to make more money. So the optimal value of c is the biggest one that just comes down and kisses this region, this feasible region. And if this region is this kind of polygon, that means it's going to intersect at a vertex. It's actually possible that it aligns exactly parallel to one of the sides, and thus an entire side would be equally considered the maximum, in which case the vertices along that side would also be it. So regardless, the vertices are always going to be my maximum value. And actually, likewise, for the minimum value, I could ask the question, what happens if c is equal to 0? That's the smallest value of c that still touches the feasibility region. Everything else is just not possible. That's my minimum there as well. Okay, so let me summarize what the big idea is. If I have a linear function, that's what we've been talking about, and I'm trying to figure out what are the extreme values of that linear function, and they are subject to a series of linear inequalities. Well, if those linear inequalities look something like this, they make what we refer to as a concave. That means it sort of closes in on itself, bounded, so it doesn't blow off to infinity. If that's your feasible region, then the extreme value of your linear function will occur at a vertex. That's the big idea of linear programming. And so this gives us a method. If you have such a system, you compute what all the vertices are. I showed you how to do it in this video. And then whichever of those gives you the largest value of the function, that is going to be your maximum. Alright, I hope you enjoyed this video. Please do check out the Maple products down in the description if you found those to be interesting. Give the video a big like for the YouTube algorithm, because YouTube likes algorithms just as much as us mathematicians do. If you have any questions, leave them in the comments below and we'll do some more math in the next video.
In this video, I will be solving this LP problem in Desmos. Go to desmos.com. Click Graphing Calculator. I'm going to begin with the first constraint. On the left here, I'm going to type 2x plus y. Then I can click the keypad icon here and click the less than or equal sign. Or I can also do that on the keyboard by typing less than sign followed by the equal sign. Then 40. Now I'm going to zoom out by clicking the minus button a few times. I can click anywhere on the graph and drag to the position I want. I can also press Ctrl and scroll on the mouse to zoom. Now I want to keep the graph in the first quadrant because of non-negativity and also get rid of this overflow here. I'm going to type curly bracket, then x greater or equal to 0, close the bracket. Then do the same for y. And this looks much better. Next, I'm going to copy the first constraint and paste it on the second line for the second constraint. That one is 3x plus 4y less than or equal to 120. I'm going to paste on line 3 for the third constraint as well. That one is y greater or equal to 4. Now I can see that the intersection of the three constraints is this region here. If you're not sure, you can hide one constraint at a time by clicking on the circles here to see what's left shaded. Since I now know where my feasible region is, I can change the constraint signs to equality to remove the shaded regions so I can better see the lines. I'm going to Ctrl scroll to zoom in. Next, I can view the coordinates of the corner points of the feasible region by clicking at each corner and holding for about 2 seconds. If you don't get the actual intersection point, just click and hold again. Now, if we want, we can evaluate the objective function at each of these points to determine which of them is the optimal solution point. On the other hand, we can add the objective function line as well. The objective function is 2x plus 5y. We can make it equal to any letter, say z. If you see add slider, just click on the letter z and it will automatically create the slider. You can see the z slider line down here. If I slide up and down, it doesn't move much because the range is from -10 to 10. I'm going to click on the 10 here and change the upper limit to like 300. Now I can slide much beyond the feasible area. Since this is a maximization problem, the highest point the objective function line touches before leaving the feasible region is the optimal solution point. So the optimal solution occurs at x equals 0 and y equals 30, and the corresponding objective function value is 150. We usually draw the objective function line as dotted line to distinguish it from the constraint lines. So I'm going to click the settings icon here, click the objective function circle, and select dotted line. I can also change the color by choosing any of the options here. I'm going to put it back in purple and click Done. Let's hide the objective function line temporarily. Now, suppose this were a minimization problem where all constraints are greater than or equal to constraints. Then the feasible region will be to the right here. I can then click and hold the corner points for about 2 seconds to reveal their coordinates. Note again that you might need to click more than once to get the intersection right. You can then substitute these values into the objective function to determine the minimum. On the other hand, I can turn on the objective function line, then slide it down till I touch the lowest point, which will represent the optimal solution point. Note that the objective function value at this point is 89.333. 90 is displayed here because the objective function is not exactly at the intersection point and because the slider is not displaying decimals. Finally, suppose the objective function is 12x plus 5y. Then the optimal solution for our initial maximization problem will occur at 418 here. And for the minimization problem, the optimal solution will occur at 040 here. And that's it for this video. Thanks for watching.